So this series can used to check whether the estimated W is not a UAVE. Okay. And next theory is the most important one is a neighborhood fit theory. Neighborhood fit theory. So it says if you have an unbiased estimator, then you condition on the compare sufficient statistic, then it's a UAVE. And there are two main ways to find a UAVE. One is you find a function phi such that the phi t is unbiased. Okay. Then the phi t is UAVE. Okay. Another one is you find unbiased estimator, and you you calculate a conditional expectation. So there are two ways. Okay. Okay. Any questions so far?
What is the purpose? So the second way, what exactly are you doing?
Okay.
Like you find a unbiased estimator,
Yes.
and then why do you want to calculate the conditional expectation?
Okay. That's because this one is UAVE by the
Okay.
name surface theory. Okay. Because this is a function of t, a function. It's a function of the complete execution statistic t, and it is also an unbiased estimator.
I see. Okay, thank you.
Yeah, that's a great question. Yeah. Okay, so now let's try to do some questions. In the first question, you have a Bernoulli distribution. So S1 to Sn. And we want to find a UAVE for following parameters. So it's this. And in this question, I suggest you to use the second method. So like this. So find. Okay, and first let's say we know that the S bar is completely sufficient for P. So you don't have to check this. Just use this result to find a UAVE. And I'll give you around 10 minutes to solve question 1.
I have a question.
Okay.
Does W need to be a function of X bar?
Yes.
Um,
Or you can be a function of summation xi. Yeah.
okay, so T is X bar here.
P.
No, T.
Yes.
So I'm a bit confused because if W is a function of T, then the expectation of W given T is, I mean, it's not random anymore, right? When you given T, W is not random anymore.
Actually, it will be a function of t, and t is random, so it still be random.
Oh, okay.
Yeah, t is random. Yeah.
Okay. Okay, I see. Thank you.
Okay. So let's see. Okay, I think let's go through the question 1. So in question 1, we have S1 to Sn, then balloon P. Okay. And we know that S bar is complete and sufficient for P. Okay. So we are to make T equal to this. Okay. Okay, T equals to this. A, we want to find the U and UE for P to the power n, and n should be smaller than n. Is that true? Yes, okay. So the first step, we find an unbiased estimator. So in this case, I would do like this. S1, S2, Xn. Because they are independent, so this is equal to power P. Okay, so this is P power M is P to N. Okay. So second step, now we have an unbiased estimator. So we want to find a function, find this. Okay. Find T. Okay, let's say T is equal to T. How about t is equal to t divided by n? Okay. So in this case, the summation of Si equal t. Okay. Okay. Okay, so now we have this. Okay. The first observation is that t should be larger than n equal to n. So if t is smaller than n, then one of these must be 0. So the expectation will be 0. Okay. Okay. Another one is, okay, this is equal to okay, like a probability of S1 Sm now equal to 1 and condition on okay. Then the conditional probability we know it can be written as this. And divided by the modular distribution. Okay. And we know this one. This one is the binomial. So it should be n choose t, p to the power t, 1 minus p to the power n minus t. Okay. So this is because summation si is followed by binomial np. Okay. And the numerator is okay. The numerator is S1 Sm equal to 1 summation Si I from n plus 1 to n equals t minus n. So we already have the first m is equal to 1. So the rest of length should be equal to t minus n. And then we can use the independent. This is equal to p plus p SP now n of length. And this one is a binomial distribution, so it should be n minus m, choose t minus m, p to the power t minus n, 1 minus p to the power n minus t. Yes, n minus m minus t minus n, so n minus t. Okay. Okay. So the whole term must be p to the power n, p to the t minus p minus n, and the denominator is this. Okay. So we can get rid of these two. The answer is okay. Also, we have an indicator, so the t should be larger and equal to n. Okay, so this is our okay, this is a UMUE. So we may want to write it to the our t is n times t, so n times t minus n times t, n choose n times t, indicator function n times t larger than n. Any questions so far?
Can you explain the last step?
This one?
Well, no, I mean, I understand exactly. Yeah, the moment you put the end there.
Oh, okay. So see, because originally I assumed t is this one, and say the t equal to small t divided by n. Yeah, I know the notation is confusing.
Okay.
How about we say this one is summation of si? Okay. So in this case, this would be t equal to t. Okay. So here we don't have n. Okay. Yes. Yeah, that would be better. Yeah.
Okay. Thank you.
Yeah. Okay. Okay, let's go to question 2. So basically, this question we always use the same technique. So here we want to find this probability S1 plus Sn equal to K. Okay. So this one, you can calculate this. This is equal to n choose K, m choose K. And also we have the p to the power K, 1 minus p to the power n minus K. So this is constant. So if we only have to find a UAV for this one. Okay. So I would define this. First step, I define S1 xk 1 minus sk plus 1 to 1 minus xn. So this is equal to this. Okay. So we get our unbiased estimator. So the second step, we want to find the conditional expectation. conditional on the t equal to t. Okay. So also this is equal to the probability of S1 sk equal to 1 by sk plus 1 sm equal to 0.
Are we using the notation that capital T is equal to x bar right now, or capital T is equal to the sum of the xi's?
Let's use this. Okay.
Okay.
Yeah. Sorry for changing the notation. Yeah, figured out this one is much easier. Yeah.
That makes sense. So
Yeah.
because x bar is a complete sufficient statistic for P, then just multiplying by n is still a complete and sufficient statistic.
Yes, because it's a one-to-one function, so it's maintained a completeness and a sufficientness.
Okay, thank you.
Yeah. Okay. So this is a summation xi. So this is equal to this. So the same, we can write it using the property of conditional probability. This is equal to and here we have the summation xi. So we can say I from n plus 1 to n equal to t minus k. Okay. Because we have k of length is 1. So the rest of length should be t minus k. So here we may have the indicator function. T should be larger than or equal to k. And divided by the modular distribution, summation xi to t. Okay. So now we calculate the numerator will be p to the power k, 1 minus p to the power n minus k. And this one is a Bernoulli distribution, so it should be n minus m, choose t minus k, p to the t minus k, 1 minus p to the n minus m minus t plus k. And the denominator will be this, n choose t, p to the power t, 1 minus p to the power n minus t. So you may realize we can get rid of this this term and this return. Okay. Here's the indicator function. So we will have this. Okay. So the UNV is n minus n, t minus k. Okay. So we usually use the lower case to represent a fixed number, but the capital case represent a random number. Yeah. This is fixed. This is random. Okay, so next is the second one. The third one is the, okay, summation 1 to n plus 1, not to the Sn. Okay. So we have probability of S1. Okay. Larger or larger equal to, okay. Okay, let's do some calculation first. This is equal to probability of S1. Is any good? Okay, anyway, I do this way. Okay. Larger than 0, multiply Sn equal to 0, and plus another one. Larger than 1, and probability of Sn equal to 1. Okay. The first term is equal to 1 minus the probability equal to 0. 1 minus this is equal to 0. So it should be, yes, p to n minus 1. That's p. Okay. No, that's 1 minus p. Okay, sorry.
Wait, shouldn't it be 1 minus p to the n minus 1?
Oh yeah, sorry. Okay, is any this a good way to? Okay. Oh yeah, I think you can do this in this way. Okay. And the second one is the, okay, it will be 1 minus, so equal to 1 and 0. So it should be minus 1 minus n minus 1 times p, 1 minus p to n minus 2 p. Okay. So this is one, they are all 0. This is one of them is 1. Okay. And we can have this. Okay. We expand the equation plus p and minus p 1 minus p to n minus 1. So this way will be very crazy. Okay. It's p squared. Okay. That's what we have. So the p can be canceled. So we will have this 1 minus n minus p to the 1 minus p to the power n minus 1 minus n minus 1 p squared. Okay. And from the B, we know that we can find U and V for this one, this one, this one. And the linear combination of U and V is also a linear combination. It's also a U and V. So for these three ones. Okay. So you just plug in the UAV you found in the quadrant B, and you use a 1 minus this, and that will be the UAV for the quadrant C. Okay. So linear combination. Also, for the linear combination, of the parameter. Okay. Okay. That's all. So we can. Okay. Any questions so far? Okay, I think that's a long question. So basically, this question have two steps. When you find an unbiased estimator, then you have to reduce, and you have to find the conditional expectation. Okay, we have 25 minutes. Okay, let's look at the question 2. Okay. In question 2, we have an exponential distribution. So this means the distribution is like this. The density is exponential indicator of x larger than a. Yes. So that implies the S1 and S bar are complete and sufficient for A and theta. And in this question, we want to use the second way. Use this way to find UNVV. So question 2. They are exponential and theta. Okay. First one is when theta is long. Okay, theta is long. We want to find U and U for theta. Okay. When theta is long, the S1 is the complete sufficient for A. Okay. And want to find a function of F Si S1 such that it is unbiased. Okay. So first, let's find this. We know that this one, this is exponential little theta n. Okay. So the average of this will be theta divided by n. So the S1 minus theta 1 is equal to A. And this is unbiased estimator. Okay. It's unbiased. This unbiased is also a function of a complete and sufficient statistic.
Why is x1 minus a? Why does x1 minus a follow an exponential?
Oh, okay. So we have S1 to, if this one is follow exponential little theta, then the smallest one is follow the exponential n theta.
Oh, okay.
So I minus A first to change to this. Okay.
Okay.
Yeah. So we find a function which a statistic which is a function of a complete statistic, complete sufficient statistic, and it's also unbiased. Okay. By the naming Sheffield theory, S1 minus this is UAVE. Okay. The second one is the when A is long, theta. Okay, it's unknown. In this case, S bar is the complete sufficient for theta. Okay. So the same, we will find the average of this, which is equal to S plus theta. Yes, because this minus A, S bar minus A, now follow the exponential distribution. So this is the average is theta. Okay. So then we imply that the S bar minus A is UAVE. Yeah. So by the Lehman-Sheffield theory, S bar minus A is UAVE. And the last one is when both of lengths are unknown. Okay. In this case, S bar and S1 complete and sufficient for theta and theta a. We do this, but this pair is complete sufficient for theta and a. Okay, so they will be a little bit complicated, but we use the same idea. So we find the mean of this, also the mean of S1. The mean of S bar will be, we know that is A plus theta. It's A plus theta divided by N. Okay. So we can say, we can use a thing like this. S bar minus S1. This is theta minus N theta. Okay. So this is 1 minus this N minus 1 theta. So the N minus 1 N S bar minus S1 is unbiased. Theta. So by the naming Sheffield theory, this is UVE. Okay. Then we do the same thing for A. So we have to multiply N for this one. So we may have the N x1 minus S bar. This might be N minus 1A. So the NS1 minus S bar divided by N minus 1 is unbiased for A. By the naming Sheffield theory, this is the UVE. Okay. Any questions so far? Okay, if you don't have a question, let's do the question 3. In question 3, we have a UVT for theta. And we want to show that the T to the power K is a UAV for the K moment. Okay. So in this one, try to use this theory. Okay, try to use. Okay.
So if this is, can I ask a question just about if this is true, then does that mean that if we have a UMBUE of some parameter, then any polynomial function of the UMBUE will be of the UMBUEs will be a UMBUE of the polynomial function of the parameter?
No, it's not a parameter. is the k moment for the t. Yeah. So this may not be this. Okay.
Oh, I see. Okay. Okay.
Yeah, that's a good question. Yeah. So let's try to do this. Okay, let's go through the question 3. The question 3, we have T is U and VE for theta. And we want to find this. Want to show that for this, for AVK equal to 1, 2, 3, okay. The first, we know that the TK is on base for this. And second, because T is UAVE for theta, so by the theorem 7.3.20, for OW, which is minino, that will imply that the TW is 0. Okay. Okay. Okay, and that's for this. Let's check. That's K equals to 2. Okay. We want to show that this for W this. Okay. So given any W which is unbiased for needle, then okay. Want to know this question mark. This is equal to TW. From the previous discussion, we know that TW is unbiased for needle. So then we can apply this again. Okay. Minus star. This is 0. Okay.
Wait, why?
Okay.
Oh.
Yeah. So first, you know that for AVW, it's unbiased for needle. TW is 0. So that means the TW also unbiased for needle.
Oh, I see. Okay.
Yeah. So you plug in W as the TW, then you apply star again, then you can get this needle. Yeah. Yeah. So that means then we can apply by the 7.320. The t square is UAVE for this. And then we continue to do k equal to, k equal to 3, 4, 5, Okay. Yeah, so this algorithm can only make sure the integral value is UAVE. Yeah. So k can only be 1, 2, 3. Yeah. Okay. Any questions so far? Okay. So if you don't have a question, let's do this discussion. And if you need any help, please let me know.
Thank you so much.
Yeah, you're welcome. Thank you. Okay, you're welcome there. Enjoy.